Hi there, and thanks for clicking on and watching. Hopefully you've done so because you're sitting Maths A Level Edexcel this summer. Paper 1 is the 7th of June. Here is a list of all the topics that are going to be on Paper 1, and I have made a series of videos, 2 for each of the papers, with a walkthrough with an example for each of the topics. In this video, I'm now just going to look individually at some of the topics, and this video I have chosen to do a quick one on proof. So let's get into the video. So we're just going to get started on this video on proof, but where is your revision at the moment? How's it all going? Hopefully you are finding things like this video helpful, because I do find it's easier to follow along with somebody on the screen rather than just reading a textbook. So if you are finding this video helpful, please do like and subscribe. Keep an eye out for any more videos that I post, and I really do hope that they are helping with your revision. So let's talk about proof. Often pupils do find proof questions really challenging because they're all different, lots of different aspects of maths are involved. They do all follow a similar sort of pattern. You do have to start with a statement, make some assumptions, follow some maths in a logical, sequential way, and then end up with your conclusion. Now, there are 4 types of proof that are examined at A level. 3 are AS level, and they are proof by deduction, proof by exhaustion, proof by counterexample. Then proof by contradiction is taught in the upper 6, that's an A2 topic. So you are going to be sitting, if you're sitting the full A level, an A2 exam. So I would think proof by contradiction is highly likely to come up. I don't know what's going to be on the paper, but I would definitely be looking through some proof by contradiction questions. So let's have a look at some different types of proof. So proof by deduction first. We've got an example here. Prove that if 3 consecutive integers are the sides of a right angle triangle, they must be 3, 4 and 5. Well, 3, 4 and 5 are the only consecutive numbers that fit into Pythagoras' theorem, and if we've got a right angle triangle, Pythagoras theorem must apply. So we've got an incorrect proof and a correct proof. So what you are doing when you are proving, you must end up with the answer 3, 4 and 5. So the incorrect proof has started with the answer 3, 4, 5, and that is really just shown that those numbers do fit into Pythagoras' theorem. So that is not proving it, that's just showing that it works. So the correct proof is to start with some algebra. If we call the first number x, then if they're consecutive, you'll have x plus 1, x plus 2, putting them into Pythagoras' theorem. So x squared plus x plus 1 all squared is equal to x plus 2 all squared. Solving that, taking everything to one side, you can see that we're going to factorize that quadratic, and we'll get the answer x equals minus 1 or x equals 3. Well, x can't be minus 1 because the values that we're finding refer to the side on a triangle, which can't be negative, so x has to be 3, so therefore the other sides are 4 and 5. Here's another proof by deduction question. We're being asked to prove that this quadratic is positive for all values of x. Now the trick when you're doing this is to complete the square. So writing that quadratic expression in completed square form, we'd have x plus half the b position, so that would be 2 all squared. That would give us x squared plus 4x, but it would give us plus 4. So we have to take the 4 off and bring down what we do want. So that would be x plus 2 all squared and then plus 1. Now thinking about this first bracket, anything squared is going to be either a negative squared or a positive squared, and it's always going to be positive. So x plus 2 all squared is always greater or equal to 0. So it's always positive or equal to 0. Sorry, it would be equal to 0 when x is equal to minus 2. So therefore, x plus 2 all squared plus 1 is going to be 1 more than this, which the lowest value that could go would be 0. So this is going to be greater or equal to 1. Hence, the x squared plus the 4x plus 5 is greater or equal to 1, and it's going to be definitely bigger than 0, so therefore it is positive. Next part, prove that the sum of the squares of two consecutive odd numbers is 2 more than a multiple of 8. Well, when we want to ensure that a number is odd, we can choose a letter, maybe n. 2n would make it even, and 2n plus 1 would make it odd. Now, you can have a consecutive odd number, would have to use the same letter n. You could have 2n plus 3, that would go 2 more than that given one, or you could have 2n minus 1. Now I'm going to use those two, and I've got to square them and add them. So 2n minus 1 all squared plus 2n plus 1 all squared. That's going to be 4n squared minus 4n plus 1 plus another 4n squared plus 4n plus 1. So this is going to equal 8n squared plus 2, which is 2 more than a multiple of 8. So let's now have a look at some other types of proof. So proof by exhaustion. When you're proving by exhaustion, you split it up into individual smaller cases, and as long as you prove for all of those, then it's proved overall. So what if we had n was an integer and we had to prove that when we had n squared plus n, it is even for all n. So you split it up and look at whether n is even or odd. They're your smaller cases. So when n is even, you would have even times even, which would be even, and we're adding n back on, so that's another even. So overall, that would be even. When n is odd, if we're squaring an odd number, you're going to get odd. And then if you add another odd, odd plus odd is going to give you even. So therefore, n squared plus n, for whatever type of n you put in, whether it's odd or even, it's going to be even for all integers n. When you're disproving by counterexample, as long as you can find just one example that it doesn't work for, then you've disproved it, that it's not going to work. So in this question, disprove the statement that n squared minus n plus 41 is prime for all integers n. Well, you can try and put some numbers in. If n was 1, you'd just get 41, which is prime. If n is 2, you'd have 4 minus 2, which would be 2, add 41, which is 43 is prime. So it's looking like it's working for some of the beginning numbers, but the number to plug in, to substitute in, is that n is equal to 41. Then you would have 41 squared minus 41 plus 41. The 41s would cancel, and 41 squared is obviously a bigger number, and 41 itself will divide in. So 41 squared will have itself and 1 as a factor, but it will also have 41 as a factor, so therefore it won't be prime, and thus the statement is not true. Here's an example of a proof by contradiction question. So when you're proving by contradiction, whatever you're trying to prove, you start with a statement that says we are assuming that that is false. So if we're trying to prove that root 2 is irrational, we start with a statement to say that root 2 is not irrational and therefore it is rational. So here's our statement. Root 2, if it is rational, must be expressed as a fraction a over b, where a and b are both integers and a over b is in its simplest form. It cannot be divided further, and that would tell us that we had a rational number. So what we do is we cross multiply and say that b root 2 would equal a, and then if we square both sides, we would get that 2b squared is equal to a squared. Now this tells us that a squared is even. Because of this 2 in front, then this expression on the left must be even. Anything doubled must be even. Now, if you think of numbers that are squared, when you get an even answer, say 36, it means the number that you've squared is also even. So this tells us that A is even. Now, if A is even, say 10 is an even number, then A could be also equal to 2k. So if A is 10, then the k would be 5. So A can be divided by 2 and can be expressed as 2k for another integer k. And we don't need to know what k is, but now we can go back to our original statement and say 2b squared is equal to 2k all squared, because that's what A is. So let's multiply that out. 2b squared is equal to 4k squared. So that is telling us that b squared is equal to 2k squared. And this now tells us, because b squared is double something, it tells us that b squared is even, which tells us that b is even. So we have now shown that through that working that A over B, both A and B are even. So this is not in its simplest form. It could be cancelled down. So here we've contradicted ourselves. If we were saying that root 2 was A over B, with A and B both being integers and A over B being in its simplest form, through this working we've showed that that is false. So therefore root 2 cannot be rational. So if it's not rational, it is therefore irrational. Here's another proof by contradiction question. We're being asked to prove that there's no positive integers, that when we put p and q into 4p squared minus q squared and get 25, there's no positive whole numbers that will make that equation work. So because you're doing proof by contradiction, your opening statement will be that you are going to assume that there are positive integers p and q to make that work. So you can try a few numbers in and see if it works, but you won't be able to find any. But we need to prove that. So on the left hand side, another way to write that would be, because it is the difference of two squares, 2p plus q, 2p minus q. Now you'd either spot that or you wouldn't, and just expressing that left hand side, it's still going to equal 25 on the right. Now because you've expressed it like that, because we're saying that there are positive integers, we are assuming in our opening statement that p and q are positive integers. Now we don't know what they are, but if they are positive integers, if we double p and add q, that's still going to be a positive integer. If we double p and minus q, we don't know it's going to be positive, but it's definitely going to be an integer. So if the first one's positive, the second one would have to be positive, because two positives will make 25. If the second one was negative, we're not going to get plus 25. So what we can think of now is numbers that actually times together to equal 25. So what numbers could they be? You could have 25 times 1, and you could have 5 times 5. They both times together to give you 25. So if we just set up some equations, 2p plus q equals 25, then 2p minus q would have to equal 1. Or the other one is 2p plus q could equal 5, and 2p minus q could also equal 5. So we've got two lots of simultaneous equations. So you could add or take them away, because you've got the same with the p's and you've got opposite signs with the q. I'm going to add them and get that 4p is 26. So P is going to be 6.5, which is a contradiction. If we put 6.5 back in, double 6.5 is 13. Q would have to equal 12 to get us down to 1. So this is a contradiction. As P is not a positive integer. Now let's do the other one. We can add them as well and get that 4p is 10. P is going to equal 2.5. If you put 2.5 back in, double 2.5 is 5, then Q would have to equal 0. So this is also a contradiction. As P and Q are not positive integers. So therefore we've got a contradiction overall. We haven't found a P and Q that does work with our assumption, so therefore we have proved. Okay, here's my last question on proof, using proof by exhaustion in the first part and proof by contradiction in the second half. So let's do or part 1 first. So proof by exhaustion to show that n, and then this means belongs to the natural numbers. Natural numbers start at 1 and they just go up, but we have n also being equal or less than 4. So n has to be, n can take the values 1, 2, 3 or 4. So proven by exhaustion, we've only got 4 cases to show. So let's put n equals 1. So then you'd have 1 plus 1 cubed, which is going to be 8, and 8 is greater than 3 to the 1, as 8 is greater than 3. N equals 2. You've got 2 plus 1 cubed, which is 3 cubed, 27. 27 is bigger than 3 squared, as 27 is bigger than 9. N is equal to 3. 3 plus 1 cubed, which is equal to 64, and 64 is bigger than 3 to the 3, as 64 is bigger than 27. We're getting the idea now. N is equal to 4. You've got 4 plus 1 all cubed, which is going to be 125. 125 is bigger than 3 to the 4, as 125 is bigger than 81. So as long as we've done it for all the cases, we have proved by exhaustion. Part 2, we've got to prove by contradiction. Now it says given that m cubed plus 5 is odd, so that is given. We can't change that. Use proof by contradiction to show using algebra that m is even. So given that we've got an odd number into this expression, we need to show that m has to be even to make that work. So our contradiction is going to be, given what we can't change, m cubed plus 5 is odd, assume m is odd. Now we just need to put m equals m is an odd number into this expression and show that we get an even, so then we've contradicted ourselves. So if m needs to be odd, we can let m equal 2n plus 1. So then m cubed plus 5 will equal 2n plus 1 all cubed plus 5. So I'm going to use the binomial expansion. You could write those 3 brackets and multiply them, but I'm just going to use the binomial expansion. So that will be 2n all cubed plus the coefficients from Pascal's triangle. We'd have then 3, 2n all squared plus 3 times 2n plus 1, and then plus the 5 on the end. So this is going to be 8n cubed plus 2 squared is 4 times 3, 12n squared plus 6n, and then plus 6. Now this is going to be even because we can take a 2 out, so then this will be 2n cubed plus 6n squared plus 3n plus 3. So this is even. So when we put an odd number in, we got even, and we've contradicted ourselves. So therefore, we have proved that it must be even. This is a contradiction. So M must be even. There we go. Well done. If you're still watching at this point, you've got to the end of this little video on proof. Proof is quite a tricky topic, and I would advise you to go and have a look at some more proof questions. Proof is on both of the papers, so you're definitely going to be asked to do some proof. Do like and subscribe if you found the video helpful, and good luck with the rest of your revision. If you've got any feedback, you can leave comments below the video, and I will see you on the next one.